Blow molding is a manufacturing process that used to create hollow plastic part by inflating a heat tube until it fills a mold and forms that desired shape. It is a molding process in which air pressure is used to inflate soft plastic into a mold cavity. It is an important industrial process for making one-piece hollow plastic part with thin walls such as bottles and similar containers. The advantage are it's a very cheaper process than injection molding multiple product method, which is used for producing reticule in large quantities. The disadvantage is limited to hollow form and the wall thickness. This project is dedicated to investigation on simulation on polypropylene using the different diameter of parison and wall thickness distribution using ANSYS software. ANSYS software has the ability to detect contact between a free surface and a wall that occur over time. This project will use the plastic material which is polypropylene. Polypropylene is a common plastic used for blow molding. It offers many advantages over other blow molding resin. A high heat dissolution temperature allows it use in hot field application. The ability to be autoclave without excessive haze or color development enabled to be used in medical application. It also has excellent environment stress cracking resistant as well as chemical and solvent resistant. Polypropylene has a good contact clarity, low color, and very low moisture transmission rate, all of which make it ideal for blow molding application. The statement of this project is customer demand, traditional technique processing, large and one flash and cavities, limited data and journal, computer simulation, and also can improve material properties and otherwise reduce costs. The objective of this project is to design and simulate the different parison diameter via ANSYS Polyflow software, and then to analyze the effect on the final wall thickness with different diameter parison and stress occur, and thus to validate the result of simulation works. Scope for this project, which are first process. The process is extrusion blow molding, and then the material used is polypropylene. Simulation use ANSYS Polyflow software. The variable is 8, 10, 18 and plus 20 mm diameter of parison, and the last result analyze the effect of the final wall thickness and stress occur. In this project, the methodology phase is divided by 3. First, design mold and parison. Second, simulation works. And third, result and analyze. For the simulation procedure, which are geometry, meshing, setup, solution, and last is result. So, in the simulation procedure, we begin, click the ANSYS software. Okay. This step software discuss all the result obtained after the conducting the simulation process. So, the result will be expressed in the table, graph, and figure. To get clear view, detailed explanation of graph and figure are also provided here. So, for the first, double click at the geometry. So, at the geometry part, you can see the parison and the mold. For the first, this is go to the parison, dimension of parison. You can see the height of parison, length, and also the radius. Same between the mold. Go to the sketch for the mold, for the mold, and then after that, surface, concept, and then go to the surface from sketch. Click here, and then after that, you can see like this. And then go back to the interface of the ANSYS, double click at the mesh, and then the mesh for the first is here, and then at the mesh, right click at the mesh, insert sizing, and then pre-sizing set for the element size is 0.001 meter, and then click mesh, insert map face meshing for parison and mould, and then name selection. This is a one for boundary 1, for boundary 1, and then this is for boundary 2, for boundary 3, boundary 4, boundary 5, and last boundary 6. This is the boundary 6. And then go back to the interface of the ANSYS. Go to double click at the setup, and the Polyflow ANSYS will appear. And then click the new task, select the follow option, FEM task, time dependent problem, and 2D metric geometry. So at here, blow molding, you can see the material data, shear rate for viscosity, constant viscosity, upper level menu, density 0.606 for density for polypropylene, upper level menu, gravity is negative 981, upper level menu, and then for numerical parameter, modify the tension intensity, and then you can see the initial time value, upper time limit, initial value of time step, mean available value of the time step, maximum available value of the time step, tolerance, max number of successful step. All the value can be changed at here. Modify the initial time. At here we can change the value. And then going to the parison thickness, you can see that this is the parison thickness task. It can be edit. And then go to the tracking of material point, here, and then tracking of material property. After that, go to the output triggering, enter the step of number of step, the new value is 4. Okay, upper level menu, save and exit, and then the solution will calculate all the number of value, and the result will appear. And then double click at the result. The result will appear. You can see the result here. And then this is the contour. Double click for the contour. Location is surface body surf. Variable esteem thickness. And then default legend view. This is the default legend view. Go to the polyline. Double click at the polyline. Body list, surface body, boundary 4. Intersect with the boundary 4. Okay. And then for the time selector at the time step 4, click apply. Time step 16, click apply. Time step 28, click apply. And the last is time step for 33, and then click apply. Okay, close. Go to the simulation animation, click timestep, play the animation. So you can see the blowing process start from the step 4, move to the mold cavity, and the last is contact between the mold cavity. This is for thickness, which rate 8.048 millimeter, and the blue is 2.390 millimeter thickness. So close, stop, and close. You can see the result. Go to the chart. It is the result for the simulation between the thickness. This is the thickness. It start from 8, decrease, and then increase. It is increase because at here the thickness will increase, because at the bottom must be very strong, because the height velocity inside the bottle must want to get the bottle can be more strength to achieve the water inside the bottle. And then go to here, do again for 8 mm diameter of parison, 18 mm for diameter parison, and 20 mm diameter parison. And then here you can see it's very slow. This is the comparison between the diameter of parison. We start from 8 mm, 10 mm, 18 mm, and the last is 20 mm diameter of parison. You can see 10 and 8 mm parison, more contact between the cavity and the mold, but 18 mm and 20 mm cannot contact because the pressure cannot blow the parison to contact at the mold cavity. For the conclusion of this project, first, ANSYS Polyflow geometry offer opportunity to predict the shape and geometrical characteristic, thickness of the wall of the intended form. Second, ANSYS Polyflow software works allow for minimizing the consumption such as minimum saltiness of water. And the last, to validate the result, it can be 10 mm diameter parison is the best parison because the parison is fully contact on the mold cavity.